Hey guys, welcome back to a new video. And this session will be the second one in our series on integration. And in particular, we'll be focusing on partial integration. Because this topic requires much practice, in this video I will be solving 4 integrals step by step, explaining everything I do along the way. The timestamps for each exercise can be found in the comment section below. So with that, let's get into it. The general formula used for partial integration looks like this, although you probably also saw it in another way. And the exact reason of why this formula is true, so why this equality sign is valid, I will leave for another video. There I will derive this formula and give it a very concrete meaning, so that you don't have to memorize this very extended formula. In general, partial integration can be used in broadly 2 classes of integrals. The first class is where there's not a direct apparent product of 2 functions inside of the integral. However, we don't see any other way of how to solve these integrals. I will be solving 2 integrals of this kind. The other class of integrals is where you do have a very apparent product of 2 functions. And for these types of integrals, partial integration will always be the go-to method to solving them. I will be solving 2 integrals of this kind. So with this basic introduction out of the way, let's get into the first exercise. The first 2 integrals that we'll be solving are the integrals without an apparent product of 2 functions inside of the integral. But even so, we can use partial integration to solve these integrals. The first exercise is to calculate the integral between 1 and 2 of the logarithm of x dx. And at first you might be surprised that we use partial integration for this, because we see that in the general formula for partial integrations, a product of 2 functions is needed. However, here we only have the ln of x. However, we know that a function can also simply be a constant. So we can simply multiply this function by 1 and nothing really happens, because ln of x times 1 is simply the ln of x. However, now we do have 2 functions here, of which one function is a constant, but that doesn't really matter. Now we can do the first step of partial integration, which is identifying the f of x and the g prime of x. In exercises like this, the f of x will always be the function inside of the integral. So in this case, the ln of x. And the g prime of x, in this case, will then simply be 1. The second step is then to derive this f of x to get f prime of x. And the derivative of the ln of x is simply 1 over x. Then to get g of x from g prime of x, we have to do integration, the antiderivative. However, in this case, this is very straightforward, because we see that the antiderivative of 1 is simply x. Because if we derive x to x, we simply get 1 again, which is a very basic check. So now we have all the components that we need to fill in this formula. We have f of x, g of x, and f prime of x. So we can simply use this formula. We have that this integral of the ln of x is equal to f of x times g of x filled in the boundaries. So this means that we need the f of x and the g of x. So we get ln of x times x filled in at the boundaries 1 and 2. Then we subtract the remaining integral, which is this one, between the boundaries 1 and 2. And for this one, we need f prime of x and g of x. And in this case, we have f prime of x is 1 over x, and g of x is again x. So we see that we have 1 over x times x dx. And we see that here our integral is simplified a lot, because this x in the denominator and this x in the numerator simply cancel out. So we get that ln of 2 times 2 minus the ln of 1 times 1, which is simply this term that we filled in both of the boundaries, minus the integral between 1 and 2 of dx. We can rewrite this as 2 times the logarithm of 2. The logarithm of 1 is equal to 0, so this term drops out, minus x, which is the result of the indefinite integral dx, and we have to fill in the boundaries 1 and 2. And this simply becomes 2 times the logarithm of 2 minus x filled in its upper boundary. So this becomes 2 minus x filled in its lower boundary, which simply becomes 1. And so our final result becomes 2 times the ln of 2 minus 1. And we already have our result. So we see that we can actually use partial integration on an integral that does not immediately have the product of two functions of x, but we simply write a product of times 1 to get our second function right here. And in this way, partial integration can also be used for functions which are not direct products, but simply do not have any other way of solving. This went very well, so let's immediately go to the next exercise, which is the integral between boundaries 0 and 1 of the inverse tangent, which is the arctangent of x dx. Again, we notice that there's only one function inside of this integral, which means that we can only use partial integration if we multiply our function with simply 1 and nothing really changes. However, at this point, we can of course use the first step of partial integration, which is identify the function f of x and g prime of x. And in exercises like these, where you multiply a single function by 1, f of x will always be the function that we originally had inside of the integral, and g prime of x will simply be 1. Then, as a second step, we derive our first function, our f of x, to get f prime of x. And in this case, this simply is 1 over 1 plus x squared, which is a very standard derivative that you will have come across quite a lot. And again, this g of x is simply the antiderivative of 1, which is x. And at this point, we already have all of the building blocks that we need to use the formula for partial integration. Again, we start out with simply multiplying f of x and g of x and filling it in our two boundaries. So f of x will be the arctangent of x and g of x is simply x. And we fill this in our two boundaries. And then we subtract the remaining integral between our two boundaries. And for this, we need f prime of x and g of x. And we see that we have g of x is x times 1 divided by 1 plus x squared dx. And at this point, you might think that partial integration didn't really help us quite a lot, because this integral is also not a standard or basic integral of which you directly know the answer. However, to solve this, we can simply use the substitution method. And if you're unsure about how to use the substitution method, well, I gladly refer you to my other video where I in detail cover the substitution method. In this case, the first step is to define the substitution parameter, in this case 1 plus x squared. In the second step, we take the differential of both sides of the equality sign. So we have d of u is equal to d of 1 plus x squared, which is of course equal to 2x dx. And we can rewrite this to get it as a function of dx, which is equal to 1 over 2x du. And as a third step, we change our boundaries, because if x changes, then our boundaries also change. If x is equal to 0, so our lower boundary, this means that u will be equal to 1, because we just fill x is 0 in this equation. If x is equal to 1, our upper boundary, then u will be equal to 2. So we now have all the ingredients to solve this integral. We get, first, of course, we cannot forget this first term. We get the arctangent of 1 times 1 minus the arctangent of 0 times 0. Then minus the integral that we'll be solving with substitution. So the boundaries we know are now from 1 to 2 instead of 0 to 1. And we have x, which is this x, divided by u, which is our substitution parameter, times dx, which is now replaced by 1 over 2x times du. So we have 1 over 2x du. And of course, we see here that this x and this x, which is quite annoying, just cancel out. So we get the arctangent of 1 is pi over 4, so it's 45 degrees. The arctangent of 0 is 0, and well, we multiply with 0 either way. So we get minus 0, so this term just drops out. So we are left with this term, which is minus 1/2 times the integral between 1 and 2, and this minus 1/2 comes from this term that we just put in front of the integral, since it's a constant, of 1 over u du. And we know the integral of 1 over u du, which is simply the logarithm. So we can rewrite this as pi over 4, 45 degrees, minus 1/2 times the logarithm of u filled in the boundaries 1 and 2. This is equal to pi over 4 minus 1/2 times the logarithm of 2 minus the logarithm of 1. And we know already that the logarithm of 1 is 0. So our final solution becomes pi over 4 minus 1/2 the logarithm of 2. And this is our solution for the integral that we initially had, the integral of the arctangent of x between 0 and 1. And again, we showed that we can use partial integration even for integrals with only one function inside of them. We now go to the exercises where we have to solve integrals with an explicit product of two functions. And in this case, partial integration will always be the first go-to method of solving. The first integral in this category is the integral from minus pi to plus pi of cosine of x times x dx. And in this case, we clearly have two functions that are multiplied with one another, so we can directly use partial integration. First, we identify f of x as being x. And secondly, g prime of x will then of course be the cosine of x. The second step is to identify f prime of x, which is simply the derivative of f of x, which in this case is simply 1, because the derivative of x is of course 1. And the second part of this step is to get g of x from g prime of x. So we have to get the antiderivative. In this case, the antiderivative of the cosine of x is simply the sine of x. And we can always check this very easily by deriving the sine of x, and we get again the cosine of x. So we have again all our ingredients, and we can use the formula. And the formula starts out with just multiplying f of x and g of x and filling them in the boundaries, meaning that we have x times the sine of x, so f of x times g of x, filled in minus pi and plus pi. And we subtract from this the integral between our two boundaries of f prime of x times g of x. And in this case, this will simply become the sine of x dx. And this becomes quite simply pi times the sine of pi minus, and now we have to be careful for the minus sign, so we fill in minus pi in x, so we have minus pi times the sine of minus pi. Then we subtract this integral, and this integral is a very basic integral, which becomes minus the cosine of x filled in the boundaries minus pi and plus pi. Simplifying this, we get that the sine of pi is equal to 0. We have that the sine of minus pi is also equal to 0. So these two terms in front of it just get cancelled out. And in the second term, this minus sign and this minus sign becomes a plus sign. So we get plus the cosine filled in our lower boundary, which is the cosine of minus pi, minus the cosine filled in our upper boundary, which is the cosine of plus pi. And we see here that we actually get 1 minus 1, which is equal to 0. So the solution of this integral is actually 0, which we found by partial integration. However, at this point, I will show you guys a trick. I already knew this integral would be 0 from the start. And how did I see this? Well, if the function inside of your integral is an uneven function, meaning that if x goes to minus x, that your function also flips sign. And in our case, we know that the cosine of x is an even function because the cosine of x is equal to the cosine of minus x. But we see that x on its own is an uneven function or an odd function because if x swaps to minus x, then we clearly get a minus sign. So this function in total is an even function times an uneven function or an odd function, which gives an odd function in return. And if we have an odd function inside of our integral and we integrate over a symmetric interval, so in this case from minus pi to plus pi, or it could have easily been minus 5 to plus 5 or minus 1 to plus 1, then the integral will always be 0. So just remember that if you integrate over a symmetrical interval, so minus something to plus something, and the thing inside of your integral is an odd function, so if you change the x to minus x, you get an additional minus sign, then the integral will always be 0. And if this wasn't that clear to you, don't worry, I will have a video specifically on this topic where I go in detail why this is and also give it a very graphical and concrete interpretation so that you will never forget this trick. Let's now go to the final exercise, which is the integral between 0 and 1 of the square root of 1 plus x times the logarithm of 1 plus x dx. And at first sight, this looks like a very daunting integral because it has this square root and this logarithm, and we don't really know how to solve it. However, you clearly see the product of two functions, this square root and this logarithm. And this really calls for partial integration. And the first step of partial integration is to identify our functions f of x and g prime of x. In this case, f of x will be ln of 1 plus x, because from this function we easily know the derivative. This means, of course, that our g prime of x will be the square root of 1 plus x. The second step is to get our f prime, so the derivative of f of x, and g of x, so the antiderivative of g of x. F prime of x is quite straightforward, so it's simply 1 over 1 plus x, because this is the derivative of the ln of 1 plus x. G of x from g prime of x in this case is a bit more complicated. So what we need to find is the integral of the square root of 1 plus x dx. This can be written as the integral of 1 plus x to the power of 1/2 dx. Or similarly, the integral of 1 plus x to the power of 1/2 times d of 1 plus x, because d of a constant is just 0. So we can always write it like this. We know what the integral of something to the power of 1/2 is. This is simply the thing that we raise to the power of 1/2 times its power plus 1, so that would be 3/2. And then the power 3/2 appears in front of it, but swapped around, so 2/3. And this is just a very basic integration. And if you're unsure about how this exactly works, please go to my other video where I treat these integrals in detail. However, we now found our g of x, which is simply this function. And at this point, we of course already did most of the work because we have now all of the ingredients we need to fill in the formula for partial integration. The first term is of course f of x times g of x filled in our boundaries. So that would be the ln of 1 plus x times 3 over 2 times 1 plus x to the power of 3/2. And this needs to be filled in our boundaries 0 and 1. Then we subtract from this the integral between our boundaries 0 and 1 of our function f prime of x times g of x. So we have g of x, which is 2 divided by 3 times 1 plus x to the power of 3/2. Then we multiply this with f prime of x, which is simply 1 divided by 1 plus x. And we don't forget dx, of course. This can now simply be calculated. So we get this term first. This will become ln of 1 plus 0 times 3 over 2 times 1 plus 0, which is this function filled in the lower boundary. We subtract this function filled in the upper boundary, so that would be 1 plus 1 times 2 over 3 times 1 plus 1. And then we subtract this remaining integral, which can be rewritten as 2 over 3, which is this constant factor which we bring outside of the integral, times the integral between 0 and 1 of 1 plus x to the power of 3 halves divided by 1 plus x dx. And this is one of the nice things to have when using partial integration, because the integrals that we are left with always somehow fall into this very nice form. Because we see that we have 1 plus x to the power of 3 halves divided by 1 plus x, which can be rewritten by lowering this power of the numerator by 1, because we divide by 1 power of 1 plus x. So this can be cancelled and this 3 becomes a 1. So we get the logarithm of 1 times 2 over 3 times 1, which we know is 0 because the logarithm of 1 is 0, minus the logarithm of 2 times 2 over 3 times 2, minus this integral, so 2 divided by 3 times the integral between 0 and 1 of 1 plus x to the power of 1/2 times dx. And this integral is actually an integral that we already calculated only several minutes ago. We calculated this integral, which is this one, to find g of x out of g prime of x. And we know that this is already the solution. So mathematics is also being lazy. So if we already calculated the result of such an integral, we're not going to do it again. So we can just use this result. So we're almost there, and we get minus 4 divided by 3 times the logarithm of 2 minus 2 over 3 times this integral. So that would be 2 divided by 3, which is this constant in front of it, times this term, so 1 plus x to the power 3 halves, but now filled in our boundaries, because here we had to calculate an indefinite integral, but here we clearly have boundaries 0 and 1. So we have to fill in our solution in 0 and 1. Rewriting this, we get minus 4 divided by 3 times the ln of 2, which just stays the same, minus multiplying these two fractions, we get 4 divided by 9, times filling in this function in our upper boundary, we get 1 plus 1 to the power 3 halves, minus this function filled in our lower boundary, 1 plus 0 to the power of 3 halves. So we eventually get minus 4 over 3, the logarithm of 2, minus 4 over 9, times 2 to the power 3 over 2, minus 1. Because 1 to the power 3 over 2 is simply 1. And we will just leave it at this because there's not much more simplifying that we can do here. So to remind you, this was the result of the integral between 0 and 1 of the square root of 1 plus x times the logarithm of 1 plus x dx. And it's somewhat of an ugly solution, but well, what did you expect with such a ugly integral? And this brings us to the end of this second video in our series on integration. And I hope that you're now more familiar with using partial integrations in both classes of integrals. Now this was not nearly enough practice, and in the future I will make very long videos where I solve numerous integrals using partial integration, so stay tuned for that. If you liked the video, give it a thumbs up, and if you want to get notified by future releases, consider subscribing. And with that, I thank you for watching, and I will see you guys in the next one. Bye.